Hello students, welcome to the EPG Pathshala on Biophysics. I am Dr. Dhananjay Bhattacharya, Professor and Head, Computational Science Division, Saha Institute of Nuclear Physics. Now in this course on quantum biophysics, you have learned how quantum mechanical particles like electrons, they behave and how their orientation change or their change of motion and location in the molecule affects the structure and properties of the molecules. Now, in the earlier courses you have learned how to behave, how to tackle a small molecule where few number of electrons are there, but those are possible in the small molecules in the molecules like oxygen atom or hydrogen atom or to some extent to the molecule like ATP and etc. But in biological cells we have huge macromolecules. The macromolecules contains thousands of atoms, and for those systems quantum mechanical calculations become unimportant, and especially quantum mechanical principle is important when you have a molecule which is breaking and forming, and these are governed by chemical reaction. But in a macromolecular system, chemical reaction does not take place all the time. So in some cases at one certain region there will be some chemical reaction that may dictate the motion and dynamics of the other part of the molecule. So you want to understand how these are interrelated, how one chemical reaction dictates the motion of other atoms, or how the motion of some certain number of atoms dictate a chemical reaction to take place. So to understand these things we need a fast and easy approach of calculation of potential energy, and in this system, in this lecture we will try to learn potential energy, and in this series of lectures we will try to understand how these classical force field based potential energy can be used to understand the biological macromolecules and biological systems. So objective of this lecture is we need to calculate potential energy of a biomolecule for improvement of any molecule or any molecular conformation, or to understand structure, function and interaction of different biomolecules. Now most biomolecules are large molecules, but we know from the previous calculations how to solve potential energy or how to get the potential energy of a small system such as hydrogen atom. Exactly this can be done by solving Schrödinger equation, but approximate methods are needed because hydrogen atom is not of our interest. We need to calculate energy of a molecule, chemical compound. Now approximate potential energy of a small molecule can be calculated by ab initio quantum chemistry such as Hartree-Fock or density functional theory. Now these Hartree-Fock or density functional theories, whether it is plane wave pseudo potential based or from exchange correlation calculation using Hartree-Fock, we need to evaluate n number of huge number of integrals. These huge number of integrals, these are so huge that there are n to the power 4 number of integrals to be evaluated, where n is number of electrons in a molecule. Now for a small molecule like benzene, we have some 6 into 6, 36 plus 6, around 42 electrons. But in a biological macromolecule such as a protein of moderate size, there are approximately 200 residues, and each residue contains about 10 atoms, and each of these atoms contain around 6 to 8 electrons. So there are huge number, and so evaluation of such huge number of integrals are impossible. Now potential energy of biomolecules considering electrons also follow standard laws of physics such as Coulomb's law, Newton's law, etc. Now electrons move very fast, and hence their different treatments were necessary. They are quantized and they follow Born-Oppenheimer approximation, they follow Heisenberg uncertainty principle, but for such electronic movements generally are needed for estimating chemical properties such as chemical reaction when a molecule is breaking into smaller fragments, or two molecules are combining into a bigger molecule. So for such situations, we know that electronic rearrangement takes place, and so we need to calculate their exact and accurate energies considering the electrons also. But physical properties of a molecule, such as its shape, its size, its flexibility, its dynamic, etc., can be obtained without considering the exact positions and readjustments of the electrons, but average electron density. So we need charge interaction, electronic wave function that solved by solving Schrodinger equation or Hartree-Fock equation or density functional theory can be obtained for smaller molecules, smaller fragments, and then from these wave functions we can calculate the electron density rho at different points around the molecule from the wave function psi. Now these rhos can be used to obtain total electron density near each of the atoms of the molecule. As shown in this next slide, that in a molecule there are several orbitals. These orbitals are actually locations of the electrons, or these orbitals are obtained from the probability density of finding electrons at different locations, and these probability densities are in effect obtained from the wave function psi, which were obtained from solving Hartree-Fock equation or density functional theory. Now these orbitals mean there are these electrons, these red electrons or blue electrons, they are moving around two atoms in a covalent bond. Now these electron density on two atoms can be subdivided into different fragments as shown by the lines in between crossing the orbitals. That means these regions, part of it are in one atom, and these electrons are residing in another atom. Similarly, these electrons are residing on this atom we can consider, and we can consider these electrons are residing on these atoms. And so now we can find out sum total of the electron density in this region, and there is a nucleus with positive charge at the center. So summing up these electron density with negative charge and the density of positive charge, we can find out the net charge on this atom. Similar thing we can do for this atom, we can also do for these atoms to find out the net charge on these atoms. Definitely we have to consider these electrons and also consider these electrons. So summing over all these electrons and considering the nuclear charge located at this point, this is definitely carbon having more nuclear charge, 6 positive, whereas these are hydrogens having 1 positive. So we definitely need less electrons. We would obtain less amount of electrons at this side and more electrons coming from different atoms at this side. And so these summing up together will give rise to some partial or net non-neutralized charge on these atoms. Now in a case of benzene or methane or ethane, we know that these partial charges are nearly zero. That means whatever electrons were there on surrounding a hydrogen, same amount of proton charge also was there on that nucleus. But when there are molecules consisting of carbon, oxygen, nitrogen, hydrogen, etc., these atoms have differential electronegativity. So some hydrogen atom connected to a nitrogen, bonded to a nitrogen, may have less amount of electron as compared to the connected nitrogen atom. Same thing is true for oxygen and hydrogen, oxygen and carbon and all those. So these different amounts of electronegativities will give rise to different electron densities around different atoms, and from that we will be able to find out their partial charges. And we always see that partial charges are more positive for hydrogens, particularly connected to oxygen or nitrogen. Partial charges of nitrogen or oxygen are more negative, that is, more amount of electrons are occupied around the oxygen or nitrogen atoms, and they come from the electronic probability density around the atoms, appropriate atoms. Now these partial charges then will interact through Coulomb's law, because Coulomb's law not only dictates the interaction between atoms with net positive charge like sodium ion or chloride ion, but they also dictate the interaction between atoms which have small amount of charges. And these net Coulombic interaction is dictated by Qi into Qj by 4 pi epsilon 0 epsilon Rij, where these Qi and Qj are considered as the fractional partial electronic charge. The epsilon 0 is vacuum electric conductivity, and then this epsilon is relative dielectric of the medium. Rij is the distance between the two charges. And when we consider the Qi and Qj in fraction of electronic charge, when we consider the epsilon 0 as with the appropriate unit, and then we convert the energy in terms of kilocalories per mole, then in that case all these clubbed together comes as a constant k Coulomb, we can say, and its value is 332 approximately. So now we can say that if there are two charges of amount say 0.1 and 0.1 both, as like between two carbon atoms which are barely electropositive, and in that case their interaction energy will vary as the curve shown in the green. So they will be always repelling each other. Their energy will be very high when the distance is short. This very high positive, that means they are repelling, and their interaction energy will be close to 0 at large distance. Same thing when two hydrogen instead of two carbon atoms, one hydrogen and one oxygen atom interact. One of the oxygen atom has a negative partial charge, the hydrogen atom has a positive partial charge, so their net interaction is negative at all distances. And since these values of partial charges are high for oxygen and hydrogen, this interaction energy also you see is very high. They are shown by the red color. Now in this kind of biomolecule, as we see, there are hydrogens connected to the nitrogen in blue. There are carbon atoms shown in orange. There are oxygen atoms shown in red. And so this oxygen atom can interact with this hydrogen atom in an attractive fashion. This oxygen atom can interact with this oxygen atom in a repulsive fashion. This hydrogen atom can interact with this hydrogen atom in a repulsive fashion, and so on. So there are many interactions, non-bonded interactions, working in this short, small biomolecule. Now, the previous molecule, this molecule was a fragment of a protein molecule. It is called two linked peptide units. So these two linked peptide units were considered by Ramachandran and co-worker in the 1953 to find out the possible structures of protein, all possible structures of a protein. So we see that proteins have various types of structures, but not all types of structures are seen. Some structural features are more dominant, some structural features or some types of structure, they never appear in crystal or in any protein. So they wanted to understand those, and they had modeled this fragment, these two linked peptide units. So this is one peptide unit starting from this carbon to this carbon. This is the peptide bond and this is the CONH group. This is another peptide unit. Both these peptide units are nearly planar and they are connected to the main chain C alpha atom with a methyl group connected to the C alpha. That means this is an alanine peptide, two linked peptide units connected to the alanine. So they took this model with all torsion angles in trans orientation. Then they varied different torsion angles. For an example, they varied the psi torsion angle from 180 degree to 0 degree, and then they found that two atoms were coming very close to each other, 1.87 angstrom. Now we know that hydrogen atomic size is about 1 angstrom. So when two atoms are coming as close as 1.87 angstrom, there is some steric hindrance. Two atoms are trying to occupy nearly same seat. Same thing is true when they varied the phi torsion angle to 0 degree. These two oxygen atoms became as close as 1.26 angstrom. This is extremely high steric contact. Similarly, when they modeled a structure with phi equal to 60 and psi also is equal to 60, they got this kind of steric contact, 2.12 between a hydrogen of the methyl group and one oxygen. Now these are the impossible structures. Physically we can see. But there are many such. We showed only 3 such examples of impossible structures, but they varied all possible torsion angles or all possible values in the phi psi space as shown in this. So this is phi values, they changed from minus 180 to plus 180. Psi values, they changed from minus 180 to plus 180 degrees. And in grid of 10 degrees interval, they modeled the structure of similar type of molecule. And then they wanted to see whether any atom of this region is hitting into any atom of this region. Or that means any atom of this region is coming in close contact with any atom of this region. Now, what do we call a close contact? They analyzed all the available crystal structures of different types of molecules, may not be biomolecule, but maybe chemical molecules also. And then they found that generally a nitrogen atom can come as close as 2.7 angstrom with respect to another nitrogen atom. Or a nitrogen atom is seen to come as close as 2.7 angstrom with respect to an oxygen atom. Or a nitrogen atom to carbon atom, the distance, minimum distance they found was 2.9 angstrom. So they thought that these distances, if they consider, if they find that and the atoms of this region are all further than these above distances, then they said that these are the valid conformations, allowed conformations. So they found that these dark blue regions are only the allowed conformations here and one set of points near this region. So these are fully allowed regions. At that time, there were some crystal structure of actual proteins were available, becoming available, and they found that there are many other structures which do not fall in these regions, these dark blue regions, but they were actually seen in the crystal structures. That means they were possible. But Ramachandran's stringent criteria did not make them allowed conformations. So what was the stringent criteria? They thought that they had considered a distance, these 2.7 and 2.9 and etc. These distances probably they were considering as too stringent, too strict. Maybe sometimes the atoms, two nitrogen atoms, can come closer than 2.7 angstrom also. Now what is the relaxed distance? They calculated, analyzed all the crystal structures are available of available molecules, and they found that yes, sometimes two nitrogen atoms came as close as 2.6 angstrom, or a nitrogen and a carbon came as close as 2.9 as against 2.8 as against 2.9 angstrom. So they thought that maybe we could consider these distances are relaxed distances, partially allowed distances or extreme limit. So they said that if these were the larger distances, if two atoms are larger than this black region, these are normal limit distances, they are fully allowed region. But if they come in between two distances, this red line, then they will fall in this partially allowed region. This partially allowed region, as I will tell you little later, that these partially allowed regions are stabilized by generally some additional forces. But no distances smaller than these extreme limits are possible. That means if two nitrogen atoms come smaller than 2.6 angstrom, they are invalid or disallowed conformation. So they fall in these regions. So we have a fully allowed region. This region, we know that these are the beta sheet structures follow on this region, and the alpha helical structures of the proteins, they fall on this region. But these are also structurally available possible regions. These are specifically for 310 helix or others. These regions, they are for some left-handed alpha helix or beta turn and etc. In the crystal structures also, they found that 310 alpha helix or some variants of alpha helix, 310 helix or some variants of alpha helix which occupy phi psi values in this region, they were seen in the crystal structures. But Ramachandran's calculation from normal limit as well as from extreme limit said these are totally disallowed regions, disallowed conformations. Now, what is the reason for this discrepancy? So they found that they had taken this angle, N C alpha C prime angle, they had considered as a ideal tetrahedral angle, that is 109.5 degree. But then when they analyzed the structures of different compounds, organic compounds, they found that such N C alpha C type of bond can have various different angles also, as small as 105 degree or as large as 115 degree. So when they allowed this angle to be varied, so that means they then modeled two sets of structures and with different angles at this region, this N C alpha C prime, and then followed the same procedure of obtaining structures of all these different compounds, all these different conformations, and then calculated the allowed and partially allowed and fully allowed regions. And then they found that this bridging region between the beta sheet region and the alpha helix region, they are becoming allowed conformations. So that means in Ramachandran plot, they had considered two distances. One distance is normal limiting distance, and larger than the normal limiting distance, the energy probably is 0. They don't need any additional stability. In between the normal limiting distance and the extreme limiting distance, they require some amount of stabilizing force, and smaller than extreme limiting distance, the structures are impossible. And also they found that these angle can be slightly variable. Now, we know that we have the atoms. The atoms have nucleus at the center and electrons surrounding the nucleus. So electrons are generally supposed to be uniformly distributed about the nucleus, as shown in these top figures. But electrons are very rapidly moving elements or very rapidly moving particles, or having dual particle and wave nature. So it may happen that most of the electrons from one side is accumulated on one side. So most of the electrons from surrounding the nucleus are accumulated at one side. Now this will give rise to a dipole moment of this atom. This dipole moment obviously will induce some dipole moment on the nearby atoms also. For example, this region is becoming positively charged and they will try to attract some more electrons towards it. So the third situation will appear where most of the electrons of the nearby atom also becomes accumulated on the same side of this atom. So that means another dipole moment is formed in a nearby atom. These two dipole moments will now interact with each other. Now, formation of this dipole moment is an instantaneous process. It may happen just like that because of the rapid movement of the atoms. And this induction of the nearby atom, that is induced dipole moment, will be formed because of this. And this induced dipole moment depends on distance to the power 3. And then we know that these two dipole moments interact with each other with a interaction potential of distance to the power minus 3 also. And so combined together, we get an energy varying as distance to the power 6, 1 by r to the power 6. Now this 1 by r to the power 6 is actually an attractive potential. So this means that when the two atoms are coming closer and closer, their interaction energy becomes larger and larger. They become more and more stabilized. But when two atoms are coming closer and closer, it cannot come as close as 0 angstrom. So there are some definite limits, and that limit must be giving us some sort of this kind of interaction, which tells us that the interaction energy is rising very rapidly at short distances. Interaction energy is nearly zero at very large distances, and interaction energy at a optimal distance, which is given as R0, it is minimum. So this interaction energy or this potential energy is also called Lennard-Jones potential or van der Waals interaction. This interaction energy has very much similarity with the normal limit and extreme limit plot as shown in this figure. So that means this figure is also an approximation of the van der Waals energy as given in this figure. So when two atoms are interacting, there can be two types of interactions. One is Coulomb interaction due to the static permanent charges, partial charges on the atoms, and also due to the van der Waals interaction, which is because of instantaneous dipole moment and induced dipole moment of the two atoms. Now we know that, and also we have seen that the bond angles are not static. They do not remain always same, as like tetrahedral carbon atoms can have bond angle of 109 degree, 105 degree, 115 degree, and so on. Same thing is true for bonds also. The two bonds, their distances is not always fixed. They can enlarge. When they enlarge, the distance becomes, the energy becomes larger than the energy or the 0 point energy. They can contract also. When they contract, the interaction energy becomes again larger. So this dark line, solid line, is the actual energy calculation using high level quantum mechanics or using experiment also. But in normal situation, in a biomolecule, we do not expect such huge deformation of bond lengths to take place. And so if we consider only a short region of bond length expansion, we can think this part is a harmonic, and so the potential energy can be considered as like Hooke's law, half k bond into b minus b0 whole square, where b0 is the limiting distance when the energy is 0, and b is the actual bond length. It can be larger and shorter than the equilibrium value. Same thing is true for bond angles. These bond angles also can be variable as shown by Ramachandran plot also. And so this bond angle variation also definitely will be due to will cost some energy, and this energy is again approximated as Hooke's law type of thing. That means theta minus theta 0 whole square, where theta 0 is the equilibrium value. For tetrahedral carbon, this equilibrium value will be 109.5, or for sp2 carbon, this equilibrium value will be 120 degree, and theta can be approximately actually the value of the bond angle at that particular situation. Now, the third and most important parameter which is required to describe a biomolecular conformation is torsion angle. Now, in fact, there are these three are the parameters: bond length, bond angle, and torsion angle, which are called internal coordinates. Instead of using XYZ Cartesian coordinates of all the atoms, we can also consider these bond lengths or bond angles and torsion angles. Now, bond length is simple. It is the distance between two covalently bonded atoms. We have to consider the center of the mass, center of the atoms to center of the atom. Bond angle also is the angle between these two bonds. That means if we consider this as a vector and this as another vector, the angle between these two vectors is the bond angle. For torsion angle, we have to consider actually three things, four atoms or three bonds. So we can consider these three atoms forming one plane, and these three atoms forming another plane, and then the angle between these two planes is the torsion angle, or in some nomenclature it is also called dihedral angle. So if we see, instead of in this view, if we try to look down this central axis or along the middle bond, in that case we will see the torsion angle as this. So this is again the angle between this atom, and this atom, so this is one plane, and the second plane is formed by this atom, and this atom. And we see that in protein we have phi, psi, and omega, three torsion angles. So phi is generally n C alpha C prime n is the phi, C alpha C prime n C alpha is the psi, and this is the omega, and this is the this is the phi torsion angle, this is the omega torsion angle, and this is the psi torsion angle. So this omega torsion angle is generally 180 degree because there is a induced double bond character in this C prime n bond. So from the bond length, bond angle, torsion angles, we can also obtain the XYZ coordinates, or from XYZ coordinates we can obtain the bond length, bond angle, torsion angle, and our energy terms are with respect to bond length, bond angle, torsion angle, and also the distances, interatomic distances. Now we have already discussed how the energy varies with respect to bond, or how the energy varies along with angle. But what happens when torsion angle is varied? We see that this is a simple ethane type of molecule. In this molecule, these are the orbitals which are containing the electrons, and these are another set of orbital, and these orbitals will interact with each other. So this orbital will interact with this orbital in a repulsive fashion, because both these orbitals are consisting of electrons. So these electrons will hate to come close to another set of electrons because both of them are negatively charged. So when we change the bond torsion angle, by changing the torsion angle, we can actually push this set of electrons far from these electrons. And so we have different orientations. For example, when the torsion angle is 0 degree, the interaction between the two sets of orbitals in this atom from this atom, they are closest to each other. So that will give rise to a maximum high energy, repulsive energy. When the torsion angle is 60 degree, the electron clouds will be farthest from each other. So the energy will be 0. When the torsion angle is 120 degree, again the electronic cloud will be close to each other, the energy will be high, and so on. So this kind of curve can be expressed as this equation. The torsion angle energy is equal to a force constant into 1 plus cos 3 phi. Now this is true for ethane-like molecule, where both of these are tetrahedral carbons, so that means they have 3 atoms connected to this atom and 3 atoms connected to this atom. But when it is ethylene type of molecule, when there is a double bond in the central bond, and there are 2 atoms connected to this carbon and 2 atoms connected to this carbon. At this situation, we do not have the threefold axis, but we have this kind of situation. One type of structure is possible at torsion angle equal to 0. Another type of structure is possible when torsion angle is equal to 90 degree. Another type of structure is torsion angle equal to 180 degree. And the third is torsion angle equal to 270 degree. So that means we have some such equation, that energy phi equal to k phi into 1 plus cos 2 phi. Now for a molecule, if we had a molecule like this, ethylene-like molecule, but without this double bond character here, then this could have been one of the best conformation, this phi equal to 0 or phi equal to 180 degree. But because of this double bond character, we cannot really get a phi equal to 0 or phi equal to 90 degree as a conformation. Phi equal to 90 degree will be very much unstable, because in that case this double bond will break. So the structure with really ethylene with a double bond will have a minima at phi equal to 0, another minima at phi equal to 180 degree, and a maxima at actually phi equal to 90 degree. So this can be achieved, this kind of energy can be achieved by adding this phase angle 180 degree. So the actual potential due to variation of torsion angle of a system of ethylene-like molecule is E phi equal to k phi into 1 plus cos 2 phi minus 180 degree. So this minus 180 degree phase difference moves this conformation, conformation at 0 degree as more stable, the conformation at 90 degree less stable with high energy, conformation at 180 degree more stable with low energy, and so on. So we have 3 terms: energy variation due to bond length, bond angle, and torsion angle. In this system, one of these may be a sp2 carbon with 2 bonds. The other one can be an sp3 carbon with 3 bonds. In that case, the energy will not be like green one or the blue one. The energy can be like this one. Or when we have a ethane-like molecule with some substitution. So instead of hydrogen, if we have bromine or another methane molecule at this side, at that time also we will have the energy as like this. So this type of energy can be obtained by adding both these one term and this term together. So these two will give us an energy of this fashion. So we have all these different types of energy coming. Now the molecules we discuss, they are not static molecules. As like electrons are not static particles, the molecules also are not static, they vibrate as shown in this movie. Now this movie is obtained from quantum chemical calculation of a molecule which resembles like adenine but not really an adenine. It is a chemical chromophore for analysis of fluorescence studies. Now these, as like this hydrogen carbon bond length, all these hydrogen nitrogen bond length or these hydrogen carbon bond length, all of these are actually vibrating in normal situation, even at 0 degree Kelvin. These are 0-point vibrations. We cannot get rid of these. These are there always in any molecule. Now their frequencies are obtained from different experiments like infrared spectroscopy, or they can be also calculated from high-level quantum chemical calculation. So these indicate that these vibrations like OH or NH, they occur at a frequency of 3200 to 3600 centimeter inverse, that is a time period of about 9.8 femtosecond. The CH vibrations take place at slightly smaller wave number and with a larger time period. The OCO stretching, asymmetric stretching, they take place in this region. So from these values of the frequencies, which are sometimes measured from experiments or sometimes calculated from quantum chemistry, are converted into the actual force constant values. So these force constant values, I have given a sample one, a representative one. So for non-bounded parameters, we need the epsilon 0, that is the energy, van der Waals energy at the equilibrium value. For hydrogen, the equilibrium value R star or R0, as I used in my equation, is 3.4. The partial charges for all these atoms are for main chain atoms of protein. So their partial charges are given like this. You see that C prime atom has a high positively charged atom, and the oxygen connected to the C prime is also highly negative. The nitrogen is highly positive. The hydrogen connected to the nitrogen is highly positive, whereas the hydrogen connected to the carbons are not so positive, or the carbon, that means the C alpha atoms, are not very negative. Now in the bond length also, we see the bond lengths are as we expect, that carbon hydrogen bond length is small, 1.099. Carbon bond length is 1.49. Carbon nitrogen is 1.457. And these were obtained by fitting the experimental curves. The bond angles, we see that these angles are given in radian. You have to convert it to degrees. And we see also that the carbon-carbon bond lengths, such as C alpha, C beta bond length, their distortion energies are not very high, whereas the peptide bond length distortion energy is very high. So if you want to stretch a peptide bond length C prime N, you have to spend a lot of energy. These are the torsional force constants. So for normal carbon, the force constant is quite small, but when it comes to the peptide bond torsion angle, the force constant is very high, indicating that the peptide bond cannot convert from trans to cis so easily. Now, similar to these, there are various force fields parameters set available. There are different groups working on parameterization, or that means obtaining the force constant Kb, K theta, etc., and B0, K, theta 0, etc. for different types of atoms. These are the force fields developed by the CHARM group, headed by Martin Karplus, who got Nobel Prize in chemistry in 2013. These are equivalent values for amber force field. These were initially headed by Peter Coleman, and now David Case is taking care of these. These are the OPLS force field. OPLS also is guided by another great person. And these are GROMACS force field, GROMOS force field. So all types of force fields, different types of force fields are available. All of these are quite good. And these are quite good to reproduce properties of proteins or nucleic acids, etc. Now, for that means these force field parameters include charges, bond length, force constant, equilibrium values for any atoms which appear normally in protein, or any bond or any dihedral which appear in protein, amino acid, nucleotide, and they are regular things like ATP, heme group, and etc. But if you want to talk about some other molecule, some drug-like molecule, and you want to study how that drug-like molecule interact with a protein, then you have to obtain their force field parameter, because there are thousands or millions or billions of types of drugs, and all their parameters are impossible to modify, impossible to keep. So the first step is you calculate their partial charges by calculating wave function, and then density of electrons by density functional theory. Then obtain, if possible, experimental infrared spectroscopy, spectra of the molecule, that will give you the frequencies at different regions for different types of bonds and angles and etc. If you do not have experimental data, you can theoretically calculate IR, infrared spectroscopy, spectra by density functional theory, and then you can assign the values of force constants by analogy with the available things in nucleic acid and protein, and then you can theoretically calculate infrared spectroscopy from again potential energy, and then improve the force field parameters. Instead of 1 to 3, you can improve the partial charge also. So all these 3 parameters has to be improved, and this needs to be followed in a loop. Now these are, if you want to do everything by yourself, but fortunately there are several programs or servers available in the network nowadays, internet. This is one such server, which is called Swiss Param. In this server, if you upload the structure of your drug-like molecule, you can calculate the force fields in the charm format or for the GROMACS format. You can also use ProDRG2 server, where if you want to include, or if you want to study any drug-like molecule whose structure is not similar to any of the amino acid or nucleotide, you can upload the structure and then get the parameters from this server. These parameters they give are for GROMOS compatible parameters, or you can use this ATB, automatic topology builder, to calculate those parameters. And there are several other similar parameter obtaining programs from the programs itself. So as like Amber has a software with it which can calculate the force field parameters for any molecule. So in summary, we have discussed about force field expression, how to calculate rapidly the energy of a molecule, whether it is a small molecule or a macromolecule, and for this purpose we have made use of some force field parameters. These parameters are, and force field parameters are useful, but these parameters are dependent on the force field energy expression also. This expression energy and the parameters are not the ultimate. There are groups of scientists working to improve these methods to produce better and better agreement with experiments, and so for that they are trying to incorporate the connection between bond lengths and bond angles. They are trying to incorporate the changes in partial charges due to hydrogen bond formation, etc. So all those efforts are going on. So hopefully in near future we will get even better method of calculation of potential energy. And finally, my note is that you should remember that what all we calculated is potential energy and not at all free energy. So free energy is generally measured by experimentalists, and we are calculating potential energy, and finally we would try to understand and we try to use this potential energy actually to calculate the free energy terms. And with this I close this session, and thank you very much.